Okay. Hello, everyone. Thank you for joining me. Let me start sharing. One second. Okay. You should be able to see the first slide. Let me know yes, no, that this is working. Perfect. Thank you, Jonathan. Okay. So, welcome. This is our 67 meeting, October 15, if I get the date correctly. Um, First thing first, I pasted the Discord invite link. Feel free to grab it and use it if you want to. I'm just using it for announcement and similar things, so just FYI. Um, if you are new, welcome. Great to see you. We meet every month. Um, make Doing my best to have content every month. So we almost 6 years into the meetup since I took over. Uh, so the idea here is that we learn something new every time we meet. Sometimes I'll bring people. Sometimes it's people like members of this group. Sometimes people that I'm just make having the opportunity to bring them in and they speak. We had a lot of speakers in the past almost 6 years. If you want to speak, if you want to have anything big, small, whatever, don't hesitate. Uh, Even something that spends few minutes that doesn't require you to do a lot of work at home, like a lot of slides and all. Just feel free to approach me. I'll be more than happy to host you and learn new things. Uh, so it's about 50 minutes kind of a session. CPP quiz fun. The highlight of this talk is about data structure and algorithms, kind of featuring a C++, kind of new C++ book that I reviewed and uh, would have my opinion soon. Um, and gotchas. If we have time, I'll show you something that I've seen that might be confusing. And I thought that would be nice to present kind of a couple slides on that. Okay, so my name is Kobe. Like my official name is Diego, but no one use it. So my nickname is Kobe. I work for NVIDIA, but this is not by any means sponsored or endorsed or anything by NVIDIA. This is my private gig. We can listen to a CPP Cast 2 episodes, and I was reviewer of a great book from Dorothy, Deciphering Object-Oriented Programming with C++. Um, so let's start with fun quiz. Okay, so let me share that. Present something else. Okay, is it too small or it's fine? Hard for me to say. Hopefully it is fine. Okay, so C++ quiz kind of revamped like kind of upgraded their website. They have few, by the way, they have few new questions that I have in my queue for the next session. So I'll present them. Um, so this is C++ 23. If you remember, they used to have 17. Now they are looking at C++ 23 standard. So take a moment, take a look at that, and shout the uh, whatever you think it is correct. So okay, so Uh, it could be few things, either it's guaranteed to output, or there is a compilation error, or undefined, or unspecified. So uh, whatever you think is appropriate is just shout it. Okay, let's unpack that because it's kind of involved. So we have two functions y, which are one takes ref, one take an r value reference, and returns one and two. Uh, the first returns one, the second one returns two, and then we have three functions which are template functions. Uh, they take ref, which basically it's a forwarding or universal reference. One just call yx, one is casting it to something. Move is basically cast, and then forwarding, which is also a cast, but it's a different one. Kind of maintaining the category in the third one. So I is equal to 10. So first we call f with I. So f with I here, what do you think would be the number here? Like what do we print? F of I. 1, right? Because this is basically uh, in it's not an R value reference. It's going to bind to this one in compile time. How about F20? What do you think? What is 20?
R value.
R value. So this is F here, y of x. So this would be, it's not an R value anymore because x is an L value inside the function. So it should be 1 again. This is the confusing part, by the way. Yeah, it's an R value, but inside this function, x is now, it has an address, it has a name, and it's an L value. So it's not binding to the second y, it's binding to the first y. Okay, g of I. So g is casting that to an R value. So what would be what? So this is now an R value. So this would be probably 2. How about g of 20? Basically, it's the same thing. It's gonna be 2 as well. Okay, the last one, h of I. So h is basically forwarding that. So I is in L value. We forward, we maintain the category, so should be 1. How about 20? 20 now is an R value, maintain the category. It's not the same as what we had before with y of x, and it's since it's in R value, it's maintaining the category, so it should be 2. So this is basically a kind of a great summary. If you understand why things the way, like, you can, by the way, read that. It's very good just to read and understand like how the rules behave, because this is kind of an important, but it's more kind of it's 2 out of 3, might even be almost 3 out of 3 in terms of uh, kind of how difficult it is, um, because it's kind of more advanced and you need to understand a few things before you can answer that. Okay, so let's go back to the main thing. Okay. Okay, so as I mentioned, today we are going to discuss C++ data structure and algorithm in with C++ and C++ STL. Specifically, I was looking at this book when I was kind of thinking last month. Usually after the meetup, like starting this evening, I'm gonna start about either having someone that would present or myself. So like, what would be the next interesting thing to present that people can learn? And this caught my eye my eyes, this is relatively new. And so Packet were generous enough to kind of having let me review that. So I have the soft copy of this book. So the book in general, the book is good. Um, I think it's more on the beginner side. It's basically going to walk you through all the very important standard library containers, uh, the importance of each performance related multi-threading aspects of the containers, if any, all kind of gotchas, like what you should be aware of and understand, including containers which are acting like adapters, like priority queues and similar, uh, like other things that are acting like adapters. Um, so again, it's more on the beginner side, but there are some things which are a bit more advanced, and I'll have a mixture uh, of this kind of kind of beginners and kind of intermediate, but it not on the expert. I don't think it had a very kind of like some books are going way into the expert side of things, but I don't think this is the case, which is usually good for people that just want to just understand like what about the STL, like what they should be aware of, and so on and so forth. So this might be a good book for you. For me, it was like an intro book, so uh, I knew most of the things there, so it wasn't very that didn't give me a lot of new things. But again, for new people, it might be a very good one. It's written very well. Okay, so let's start with few things that I capture from the book, which I thought would be interesting to present. So let's start with a question: do you expose your data structure in a getter? Like you have a class, and this class have all kinds of functions, kind of methods, uh, but some of them, maybe all of them, maybe some, but part of them that just expose internal data structure as is. That might be mutable, which is bad. Might be immutable, which is a bit better. But do you do that? If you do that, just remember that that is part of your contract and it's really hard to change. So here's an example. I have an accessor, which I just a full class that I made up that returns the internal data, just the stud vector as is. It's immutable, so at least it's immutable. So because having a mutable one and relying on data races, if someone do something on a different thread and all, it's good luck with debugging that and understanding the code. But the question is like, is this okay? So sometimes it is okay. Sometimes it's okay. Like I have some computation and I just want to give away. And sometimes I might just give away something as an R value, like return copy of that and let the consumer of this result to do whatever they want to do with that. Uh, so sometimes it is. So there are cases where this is perfectly fine. Remember that containers, like STL containers, they also expose internal things, but this is by design. Like for example, stud vector, they would return reference to some index, right? So some element in the vector, which is by design because this is a container. It manages the elements and it can you can access either mutable or immutable with that. And yeah, this cause issues like the regular issue of I'm holding maybe a reference to something which is a pointer and I do push back and it's reallocating the vector and now I'm holding a dangling reference or a pointer. So that comes with some caveats. Okay. So how about thinking about thinking on exposing something else like iterators. So you need to expose an abstraction. Every case needs to be investigated if this is the right choice. But let's say there is a very good motivation to do that in your case. Why it is good? So I listed some of the benefits. Let's say you want people to uh, get the iterator as an abstraction, and they iterate, but you do something while they iterate. You do something else. Like they iterate, but you can decide that you want to do row major versus column major iteration. Maybe you want to do some data transformation. Maybe you want to multiply or add or whatever the values before they get the value. So they iterate, and every time they get a value, there is some transformation that happens on the value, but they don't know about it. Like the consumer doesn't know about it. Maybe you want to filter. Maybe you want to filter the elements, which is also a very interesting approach where people iterate, but you want to skip zeros, for example, or whatever, like whatever the use case. So this, instead of providing the entire um, container and the logic of what, like the knowledge of what they need to do in order to get the meaningful elements, instead of the consumer knowing about it, you hide it inside a producer that just provides a mechanism to iterate and get the elements. You want this iterator to function at a producer side in all kinds of scenarios, for example, range for loop and whatever other means, like regular for loop, range for loop, all of that stuff. Without going into a lot of details, the book does have a lot of explanation. It walk you through the various iterator categories, what the requirements. I'm not going over that because it's long. Uh, we'll see that there's few elements that you need to implement in your iterator in order for this iterator to function. By the way, if you know nothing about iterators and you want to create your own custom iterator, you can create a range for loop, try to compile, and let the compiler guide you through. Oh, I'm missing this. I'm missing plus plus, and I'm missing begin. I'm missing end. Like the compiler would help you to understand like what are the missing operators that you need to overload in your iterator in order to make it functional. So here's an example. Uh, Square iterator. So Square iterator is basically probably the simplest one that you can have. I would say upfront that this whole type defs at the very top of the class, they're not always required, especially not in this specific example, but this is like good practice to have them. And then you can see that the type defs are being used inside. Okay. And the one thing that I'm going to mention, so you can see that there is a deref operator here, this start, which is doing this value times value. So this is why the square iterator, it's doing square. So there are all kinds of overloaded operators uh, that you need to implement, including accessing. There is a comparison that are here. So all of that is required. I added the minus minus. It was required for me to demonstrate this to the next. I'll explain that in a second. But everything else is pretty much standard. If I didn't have stud next used here, I wouldn't be needing the minus minus. Just require that. You can see that there is a post plus plus because of the int. This is kind of a hack in my like. I know that almost, I don't know, 28 years since I learned that, and it always looked like a hack to me. And because you need to remember the pre and post, like how to, like what is pre and what is post. This is post. Um, you just need to memorize it. I memorized it. So, but it looks like a hack in the language. But this is a post increment, and you can see that it's post increment because kept a temporary and return. It's doing plus plus and return the previous value, temporary one. Anyway, and it's by value. This is why post increment is usually more expensive, and you should strive to have plus pre increment unless you really need the post. Okay, so here's what we have. We have a vector. We prime the vector with begin and end. This is like, by the way, the most basic custom iterator. We'll see a bit more advanced one, but they are all pretty much very similar under the hood. Data plus size. So I have a begin and end. I have a simple for loop. This works perfectly because I have all the ingredients baked into the iterator. And so we print 1, 4, 9, 16, 25 because we have 1, 2, 3, 4. So you can do the math. And then I'm showing here, and this is not part of the book. It doesn't show the stud next. I just want to show how stud next. There is also stud advance. Stud next returning a point. Returning the iterator that was changed. Stud advance is actually acting on the iterator that it's returning void stud advance. So I could do both. So begin is 1. I'm moving 2, so this would be 9. And then I have subscript operator position 3. So I'm taking IT, the iterator here, which is 9, and I'm subscripting to 1, which is 1. It would be 16 because I'm holding 9 in the iterator. Very simple and very useful when you actually need to expose an iterator. But you can see that it's kind of out of band in the sense that I have some vector and I'm priming my square iterator with that. But then I'm not working with this vector anymore. I'm just as long as the semantic of plus plus, minus minus, and all of that works on this pointer, my custom iterator would work. So transformation in iterator is basically baked into the operator, the deref operator that I'm showing here. It can be anything. What we had in the previous slide was just pointer like deref pointer times deref pointer, but it can be, oh, there is some iterator that points to something, and I want a member. I want to return the member. So that would be, and I'm returning a reference to that. So it can be anything. Like, just think about all the options. So you can have transformation, you can have computation, you can have skip, filter, anything that you can think of is enclosed in the iterators. This is why this is a very important pattern. So here's another example where you don't necessarily need to expose everything under the sun. Here you can see that I have a custom container. It's a stud vector, and I have begin. I have one which is constant, which is when one which is not constant, then end similar, and I have a pushback. And I just expose begin and end, and I'm not exposing anything else, but I have pushback. So there's all kinds of variations. You can do any hybrid solution that you feel that works for you. Usually you'll see in the textbooks and others this specific variant of iterator. You have this my container, which is holding something, stud vector in this case, and then you have an internal inner class iterator, and this is very common to see in many textbooks. And a begin would be, here's an iterator instance with begin, and then here's a iterator instance with and you provide everything that you need, which is this is the minimum probably that you need is plus plus, which is pre deref, and then equal equal and not equal, and it's going to work with this for loop. It's very very simple. So this is going to be the most common variant of iterators that you'll see in the textbooks. Okay. One thing that the book had, which I wanted to kind of expand on, was using void underscore t. This is a bit more on the advanced part of things related to the standard template library and facilities inside the library. So let's start with talking about Sfinet. This is substitution failure is not an error, something that I got familiar with maybe 24-ish, yeah, 24 years back. Wasn't very known back then. It's not a lot of people knew about Sphena, but it's more and more common today. Well, and it's winding down because we have other things that we can use instead of Sphena, which are more easy to understand. The book doesn't talk a lot. I don't think I saw a lot of concepts, uh, but just a bit, just mentioning, but not heavy on concepts. There are other books that would allow you to learn more about that. So the idea behind Sphena is kind of customizing the way the compiler builds the candidate list of functions. What does it mean? So when the compiler compiles your code and there is a function call, it needs to find a function, and we have overloads functions in C++, so it can be multiple candidates, it can be other, like there's a lot of things that can happen. ADL is one of them. So with Sphina, I can actually control, like, hey, I want this function to be part of the candidate list, or I don't want this function to be part of the candidate list. So this is basically why you would use these techniques. Okay, so here's a very common, there are all kinds of, by the way, textbooks and online, there's multiple ways to uh, see how, and it can be very hairy. It can be very hard to understand sometimes if it's huge, like the expressions. But here's something which is relatively easy. I have two functions. One is process that takes t as a template parameter, and another one takes the same t. But there's another thing that they have in the template parameters. So they have two template parameters. Both of them are defaulted to null pointer. So the user calling process doesn't need to worry or bother with the second template parameter. Okay, so remember that auto deduction is done by the compiler. So you pass the argument to the parameters, and it's being deduced automatically for you unless something is not cannot be deduced. There are some cases, then you need to help the compiler, but you don't need to worry about the second one. So what we have here is the following. We have this enable if, which is a struct. And then inside we have this type trait, stud is integral t, and then value. This would be eventually true or false. If t is an integral, it's going to be true, otherwise it's false. And the whole expression would yield the type, in this case be t pointer, and it's going to be null pointer. So if t is integral, the type trait succeed in replacing that, and there is and it's true, this whole thing would be something. Okay, and if it's becomes something, the compiler is happy and it's all good. If it's not an integral and this is false, the enable if doesn't yield the value. The substitution is failing, but it's not an error. So what the compiler would do, it's going to remove that from the list, the candidate list that I mentioned before. So that's the whole point. So what happened here is that if I'm calling process with an integral, it's going to pick this one. This is not going to be in the candidate list because this spina would fail. This is floating point uh, would fail because it's an integral. It's not a floating point. And only this function would be instantiated and visible to the compiler, and it's going to be picked. It's the other way around. If it's a floating point and it's not an integral, this one would be. If there is a ambiguity, the ambiguity would not in this case, but if you did something that would result in ambiguity, the compiler would tell you there is ambiguity because it cannot, like, if both of the functions are equally good, there's going to be a compiler. Here's another example. It's kind of the same idea, but instead of taking an integral like this one, if you pass t, which is a container, so if t is a stud vector of int, this would succeed. It would yield something. So substitution worked. And here, if it's stud vector and you try to substitute that this would be the is same value would be false, and it's not going to yield the type. There is no type here. This is how enable if is designed. There's not going to be a type, and this substitution would fail. It's not an error. It's just not going to, like, the compiler is going to remove it from the candidate list or not even put that as if it never exists. So taking that, here's how you can use that. So we have process containers, but we have process here. So this is process 10, process 314, and then there is a process container. We have vector of int and map of int and int. So all of that works very well, and processing integral, processing floating point, and then processing vector and processing map, just like we have here. Integral, floating point. Yeah.
Can I ask this annotation in the template, is that similar or maybe even identical if you put like a static assert within the function?
Yeah, but it would be, so if you inside the function. So first of all, it's the same. It's very similar mechanism. The question is, like, what do you want to do? Do you want the function to be part of that, and the compiler would assert, like the static assert would, like the is, but it's part of the candidate list.
Yeah.
And the assert would happen, but it's the same mechanism.
Okay.
The question is, like, what do you want to do? You want to gate it at the level where the compiler is picking building the candidate list, or it's already part of the list and it's instantiating it, and then the static assert is kicking
yeah.
in.
Yeah. I feel like the static assert is easier to understand. I don't know, but yeah, I mean, I see how you're saying you're kind of gating it earlier in the process.
Yeah, you're getting it earlier. Yeah.
Okay.
Yeah.
Okay.
By the way, I'm not showing that, but there are so many variants to what I'm showing here. Like, some would have it as a parameter, like function parameter, like for sometimes. Some would have it as the result, not the result, the return value. Like here I have void, but I can, like, there's so many variation where you can put. The main idea is that no matter where, it's going to be in the part where the compiler try to instantiate stuff in the function, and it fails. Substitution failure is not an error. It's not part of the candidate. So some people would say, oh, I want to, like, the type that is being yielded is going to be used as the return type. So there are all kinds of variations, but they all have similar, just different use cases. So you need, it looks like, by the way, I remember I used to be, before cppcon and all, there used to be a BoostCon in Santa Clara, and I think in 2006, I attended a So alongside BoostCon, there was another I think it was 2 days workshop with Herb Sutter and Bjarne, and it was 2006. And we asked him, "Hey Bjarne, what do you think about Sfina and all of that?" And he was like, "Oh no, you know about Sfina." Like he didn't, but at least back then he didn't like the fact that, because he saw that as a kind of complicated part of the language. He didn't really like that. So today we have like better ways to do that. Like concepts is a step up. Like you can hear, like if you hear people saying, "Oh, concept is kind of a better Sfina," that some people think that this is kind of like concept is a better Sfina. So uh, there was a different proposal of concept, which I think CPP cast. There is an episode with one of the either original authors or of the proposal that explain that. Uh, and there are some explanation in the web about that. So it's interesting. By the way, Justin, you mentioned static assert. There's also if const expert. There's all kinds of stuff that you can use type traits in the same context. So there's a lot of things in the toolbox.
Yeah, thank you.
Okay, so since I mentioned type trait and I mentioned if const expert and Justin mentioned static assert, so there all of these are pretty much here. So process numerical data, key data, and this is branching in compile time. Okay, so if const expert, if it's integral, this is going to compile. Everything else, no. If it's a floating point would be this line would be used. Otherwise, static assert, this is a compile time error, and we have a message. It's very useful. So you can have other crazy, or not crazy, maybe very useful stuff with if const expert. Let's say if it's an integral, I want stud greater, otherwise stud less. So you can customize, for example, how you sort things. So it's very useful. Okay, so I started talking about void. I did some kind of I showed few slides just to get you warm up on Sfina, and I'm gonna show you another option in that you can have in your toolbox, kind of the advanced one, but it might be useful, especially if you're writing generic code. And by writing generic code, I'm not saying that you are an author of a huge library that expose generic code and only generic code or whatever. You might even write just a single function for yourself or maybe for your peers, but you need this small something that that might help you. So from CPP reference, the void underscore t, it's a utility meta function. It maps sequence of type to the type void. Okay, and it is used in the context of Sfina. Prior to CPAPA's 20 concept, as I mentioned, concept of better Sfina, much better. Um, Conditionally removing functions from the candidate set. That's what I mentioned, the candidate set of the compiler. Based on if it's the expression is valid. So what's all the fuss about this utility function, utility void t? First of all, it's variadic, which means that I'm instead of doing like crazy spina with a lot of types and all, which is can be very hectic. It's variadic, so I can have multiple of them. Eventually, if everything falls in part, like everything looks good, Sfina succeed. There again, if it fails, no error, so it's not a candidate. But if it's succeed, it's gonna be void. So you can see here that and this is by the way a super useful thing that I used even before I read this part of the book. I actually needed that in one of my one part of my code, I wanted to have a this uh, I want to determine if this type is uh, can be an iterator, is it iterable. So here's the thing. So I have t whatever. Okay, let's start with the upper one. First of all, I have a variable template. Okay, I think this is a C++ 14, if I'm not mistaken. I can remember. Not, I don't think it was 11. I think 14 added that. Uh, two template parameters. We don't care about the names itself. One is type name whatever, and then equal void. So basically, I just want the user of this is iterable just to give me one type, and I'll do something with the second template parameter. So this is the main template, right? This is the main template. This is kind of a specialization that would be, so the main template is false, like this boolean would be false. This would be true. It's going to be true if Spina succeeded. If it's not, there is no such thing, and it's going to be false. Like if I give you something which failed this stud void t x y z whatever a b c whatever, like it's variadic template, right? If something fails, this whole thing didn't exist, and is iterable equal false is what you get. So when you do static assert, you get false. So if I take t, and I'll explain what decal val is doing, but I'm instantiating that because I need to have that begin. If I have that begin and it yield a type, and I can do decal type on that, and everything works. Same deal for end, that end. This void t would yield void, and we are all good. So is iterable, for example, stud vector of int would give me true, so I can put it in static assert. In a generic code, when I have a function that, a template function that gets t, or maybe a class that gets t, and I want to query, is this t something that I can iterate over? I can use this trick. Okay, so let's talk about decal val, because I don't like saying something without, like, people will say, okay, what the heck is decal val? So decal val is very, very simple, helpful utility that can be very handy. This is, I think, from CPP reference, I think this is the best explanation that I can think of, because it's very, very clear. You have two types. One is saying default, because it has a default constructor, because I didn't define anything. It has foo. I didn't touch any constructor, so default is defined, implicitly defined by the compiler. Here I deleted that. So there is no default constructor here in the non-default. There is no such thing. Now, if I want to do decal type of something, so I create an instance of default, like this is all compile time, like there is no instance in runtime, but I want to create an instance of default that foo. I want to decal type the return type of foo. Okay, and this whole decal type of default instance that foo would give me int. So n1 is int. If I want to do the same with a non-default, like think about anything that has non-default, and I'm trying to do that, that's not going to compile, because I cannot, even in compile time, the rules are the same. I cannot do that. If I have decal type of decal val, that's something else. So decal val allows me to take something which is non-default, as it doesn't have default, and I create an instance of that foo and decal type of the whole thing. So decal val is a kind of a tool in your toolbox where you say, I want to create an instance. I'm gonna invoke a default constructor. I don't know if it has a default, like empty constructor. I don't really care. I just want an instance that some function just to retrieve maybe the return type. the decal type of the function, which is going to yield the return type. So this is the whole idea of, I don't know about T anything, but I need an insert to do that begin. So I want to have the decal type of the that begin return type. So this is where decal val is super handy. If you end up with something that you don't need a decal val, that's fine. But if you're writing a generic code, you want to cover all the cases, including someone is passing something that doesn't have a default constructor, and you need it just to evaluate the in compile time some return type, for example, in this case. So super useful. Can only be used in unevaluated context, not required to be defined, which is great. It is an error to evaluate expression that contains this function, and so on and so forth. Okay. So
yeah, maybe not like immediately relevant question about the last slide.
this one.
Yeah, for the non-default struct. So if you delete the default constructor of non-default, how do you instantiate
You
this?
don't.
Okay.
Yeah. I was waiting for this question. So
Okay.
it just cooked up. They were lazy to get, but it's just not. It's not important. But yeah.
Okay. I wasn't sure if this was just like.
No, you can't. Like, there is no way to have that. There was,
Okay.
I think, there was a loophole. I need to verify. There was few years ago. There was a tweet, and I bet it's gonna be hard for me. But here's an equal delete of the constructor, but with curly braces, I can actually. And I think it was fixed later in later standards.
Okay.
So I could have a non-default. Don't quote me on that, because I this is memory from 5-6 years back. So I could have non-default. It was equal delete, and I curly braces it, and boom, I have the instance, which was kind of crazy. That should be, and I think it was fixed. So if my memory is correct, and this was the case, yeah. But yeah, you're right. If I have non-default n, this is not going to compile. There is no constructor.
All right.
This is actually good. It's relevant and a good question. I was waiting for that. Thanks. Okay. So here's another another usage of this void key. Has serialized. And now has serialized in this case using stud false type. I'll show you in a moment, like what false type is going to like how the compiler is unpacking that. So bear with me. It just creates an kind of a type. It's an integral type of false, basically yield false. So there is Hesiod, and then there is Hesiodized with void t, decal type, with decal val, and then that's serialized. So here we just have one in this variadic template of void t. We just have one. So Hesiodized of this whole thing, and then comma t would be true type. And this is just a convenient way, and you should probably follow that, because the standard library is following that. This underscore v. There are a few cases which I forget. Yeah, this, for example, I can't remember exactly some standards. Like, some was introduced in. It's a library kind of change. The underscore v. So it's shorter. Like, you can have stud is integral underscore v instead of colon value, which is shorter. So same deal here. You should make your user's life better in just introducing this has serialized underscore v. So it's just a convenient way to instantiate one of these things. Either has serialized would be true or would be false. Here there are two types. One is a person. Yeah.
Oh, sorry. I think it's C ++17 feature, right?
Yeah.
Okay.
Yeah. That's what I remember. So person has serialized, dog does not. And there is a process collection, and it has static assert of has serialized. So if it doesn't have serialized, I cannot call process collection on dogs because it doesn't have serialized. But otherwise, I can call process collection on people. People has this serialized. Static assert doesn't fire in case I pass people. So when I pass people to this function, it's going to be stud vector of people. Has serialized t of people would be going here. Decal type, this whole thing would be succeeded, and it would be a true type. So it would yield colon value would be true, and static assert would be happy. Okay, so if you are curious about like how this whole thing uh, unpacked in the compiler, so has serialized with false type is basically there's this there's a bunch of useful uh, kind of small utilities in the standard library. This is one of them, integral constant. Integral constant basically takes a constant, Boolean in this case, but can be 7. And you create it by uh, having this integral constant of int comma 7, like the type and the value, you create a distinct, like this integral constant is not a Boolean. It's a different type, but it has a Boolean inside, and there's a value to this Boolean, which is false. So it's very useful. Scott Myers, in his last book before he retired, has a lot of good stuff on that. It, uh, you'll hear it in the context of tag dispatch. So just Google tag dispatch with C++. You'll see usage of very important usage with integral constant. So this is how the compiler sees that. This is cpp inside.io. So has serialized with true would be like that, because this is person was used. And this is basically the template itself. This is the instantiation of that. So if you have doubts about what exactly happening with all this template stuff, not only templates, by the way, all type deduction, auto, use CPP Insight. It's a great, it's a learning tool and helps you to figure out like what exactly happens with your compiler. Okay, let's talk about the allocator interface. So I'll do it quickly. It's a very common kind of a domain, not used a lot, but it's everyone heard about allocators. So allocate and deallocate, think about it like malloc and free. Construct and destroy are basically construction and destruction, like constructor and destructor. So because if you think about new is allocating data and then running the constructor on the data that was allocated. Custom allocator that just call operator new and then placement new here. This is placement new, basically. And then you can plug it into stud vector. So it's this allocate, deallocate, construct, and destroy are very, very simple. There are the interfaces that you need to conform to, but it's basically kind of a policy that you pass to the stud vector. And it's going to work very nicely. This is just using new and delete. You can see that destroying is calling the destructor, and then you call the allocate will call the operator delete. Same for new. New would just create the storage, and construct is actually calling the constructor with variadic templates arguments to the constructor, because constructor can have multiple parameters we don't know. So this is very generic, and it works very well. The last part before we kind of finish when wrapping up, I'll have the 2 slides gotchas as I promised. It talks about span. It is the book. It is also mentioning MD span, but it doesn't. I don't remember it is showing anything about MD span. Span is by far one of the useful utility that we should all, it has millions of constructors to adapt to any kinds of something that is spannable. Empty span is 23, by the way. A lot of people contributed to that. ADSP has Connor and Bryce talking about empty span a lot. But span is a great tool to pass something that has a pointer and length. Note the const here, which is important. Sometimes you don't want to change anything on the payload. So having const on the T is super important. It has multiple functions like subspan and a lot of other stuff. Super useful. Unfortunately, not. I don't see it used a lot, but hopefully, uh, it should be seen more and more as we get more matured in how we use our how we use the standard library. This is introduced in 20, but if you're not in 20, there is something called GSL and GSL Lite. They have span implementation that you can use. Okay, as I promised, couple slides on gotchas. What's wrong here? Is it comparing strings? This is actually comparing pointers, not comparing string. It's a common mistake. This is actually by far a more common mistake, unfortunately. Stud map of const pointer, which is useful, but it's not doing the right thing. Why? Because map, when it's doing comparison, would compare pointers. We don't want to compare pointers. We want to compare the strings that the pointers are pointing to. So don't forget, it's okay if you don't want to have stud string, you have const pointer because you have literals somewhere and you just want to have stud map of them. That's fine, but make sure that you plug in the right comparator, uh, the compare function, into your stud map. This is a policy. By the way, just another plugin into a great book, if you kind of more the advanced, but I think super important book for the community. C++ software design by Klaus. Just Google C++ software design by Klaus O'Reilly. Great speaker, cppcon and other places. But I think one of the best design pattern books out there. Like fantastic. So it also talks about the STL and policy. Like it talks about policy strategy, all of that stuff. So it talks about this specific idea in the standard library of plugging all kinds of different policy. This is a policy to compare the strings. This is how you solve that. That's it. That's what I had for today, right on time. Do you have any questions to the material that we had? I'm going to upload the recording. I'm going to publish the slides so you can look at them. Yeah, and if you have questions, I'll be happy to take them. Otherwise, you can join the Discord. We can continue there if you have anything. That's it.
Why should we prefer concepts over the enable?
I personally don't have the opportunity to use 20, but I would definitely use 20. There is a so if you ask me, I'll prefer concept. There is a talk by a guy named Alex. Can't remember the last name. cppcon, maybe CPP now, CPP North, about his company's transition from C++ 17 to 20 using concept and how this improved their overall code readability and so on and so forth. So I personally attended the talk a couple of years ago. So just it was CPPCon, so you can take a look. It's Very approachable talk, by the way. So easy to grasp. Okay. Thanks, everyone. Much appreciated.
Thanks, Kobe.
Yeah, take care. Good to see you, Justin. Good to see you, everyone. Bye-bye.
Bye.